This episode is brought to you by Brilliant. This is the BMW N63 engine. The N63 is a range of twin turbocharged gasoline V8 engines known for its dense hot V turbo packaging, performance potential, and an accompanying range of mechanical and reliability issues. And while the N63 line isn't the most complex engine currently in production, it represents the current state of non-hybrid engine design complexity in high-volume vehicle production. Depending on its application variant, the N63 can have up to 36 primary engine functionality sensors, with up to 20 additional secondary system sensors. Vehicle-wide, the total vehicle sensor count easily surpasses 100 sensors. Driven by the push for tighter emission standards in the 1970s, the mass adoption of fuel injection in the 1980s laid the groundwork for the aggressive evolution towards a paradigm of software-based sensing and control in gasoline engines, and with it the concept of a sensing device has moved from an integrated element within a standalone mechanism to a dedicated information layer that drives functionality. What made this evolution such a technical challenge is the requirements placed on engine sensing. These devices must operate in complete unison across a broad range of operational methods, each presenting critical data hundreds of times a second while maintaining a combined total error rate of less than 3% across a broad range of temperatures, electrical noise, and vibration for a significant portion of the engine's life, and all at a cost suitable for mass production. Modern engine sensors can trace their evolution back to the early 20th century, where simple mechanical sending units that used fluid pressure or mechanical methods to directly actuate a gauge needle. Oil pressure was a common example of this. Electrical sensing, such as with ammeters and voltmeters, also worked in a similar manner, though with the use of an electromechanical coil to generate the gauge needle actuation force. By the 1930s, the concept of a remote sending unit was introduced. These devices performed mechanical measurement near the source and transmitted information electrically to a matched gauge. They were initially implemented as simple electromechanical switches that triggered a status lamp. The spring-loaded oil pressure switch was one of the first examples of this. Still found in use today, it uses oil pressure to break past a threshold diaphragm spring force in order to open an electrical circuit. More sophisticated dynamic sending units would replace the mechanical switch contact with a carbon or nickel-wound wiper mechanism that effectively allowed force to be converted into electrical resistance. Known as a rheostat, this mechanism, when placed in line with a current-driven electromechanical gauge, would actuate a calibrated needle based on the resistance created by force within the sending unit. Rheostat-based sending units were extremely versatile and could be adapted to a broad range of fluid measurement techniques. In addition to pressure, fluid levels could be measured by attaching a float to the rheostatic element. This technique, still in use today, forms the basis for fuel-level sending units. The first practical coolant temperature senders in cars also made use of this technique, though with a bimetallic element that actuated the rheostat as it expands and contracts with temperature changes. A variant of the rheostat, known as a potentiometer, would soon find its way into automotive systems over the next decade, though mostly for control sensing in various mechanisms throughout a vehicle. They differ in that the variable resistance is used to divide a source voltage relative to an applied force, allowing for direct analog or electromechanical circuit control. They also could be made in either a linear or rotary configuration, making them extremely versatile. The introduction of semiconductor temperature sensors in automobiles in the 1950s brought about the initial change from mechanical to electronic measurement. These first devices, known as thermistors, are semiconductor devices made from metal oxides including manganese, nickel, cobalt, and copper oxides mixed with binding materials and sintered into a ceramic-like structure. Their key property is the predictable, fast-responding change in electrical resistance with temperature. This is achieved through the thermal effect on electron mobility within the semiconductor material. Most automotive applications use NTC or negative temperature coefficient thermistors, where resistance decreases with increasing temperature, typically offering sensitivity around 4 to 5% resistance change per degree Celsius in the critical 80 to 120 degrees Celsius engine temperature range. The semiconductor composition allows for a highly predictable, wide response curve that can be accurately interpreted by electronic control. They're also inexpensive to manufacture in massive quantities and could be packaged easily in a broad range of configurations that allow for sensing of air, coolant, and exhaust gas temperatures. Thermistors, however, do have an operating temperature limit of around 300 degrees Celsius or about 572 degrees Fahrenheit. In cases where higher temperature measurement is needed, such as within an exhaust gas stream, thermocouples are used, though this comes at the cost of reduced accuracy. Thermocouples generate voltage when two different metals are joined and exposed to temperature differences. The voltage output is proportional to temperature, enabling measurement. Automotive thermocouples typically use chromo-aluminal or K-type for high-temperature exhaust monitoring. By the late 1960s, the lambda sensor, also known as the oxygen sensor, was introduced as the first standardized feedback-based engine management sensor. Its purpose was to help optimize engine operation in order to work efficiently with emissions-reducing catalytic converters by monitoring the oxygen content in exhaust gases. The sensor uses a zirconia ceramic element sandwiched between gas-permeable platinum electrodes, effectively forming a battery cell that varies its voltage based on the difference in oxygen levels between atmospheric air and exhaust gases. When combusted air-fuel mixture is rich, or less oxygen is present in the exhaust, it produces a voltage around 0.8 to 0.9 volts. When the combustion condition is lean or contains more relative oxygen, it produces a lower voltage around 0.1 to 0.2 volts. This voltage change occurs rapidly around the stoichiometric air-fuel ratio of 14.7 to 1 or a lambda of 1. The sensor's voltage range output is used to adjust fuel delivery, maintaining the optimal air-fuel ratio for catalytic converter operation through closed-loop feedback control. In contemporary O2 sensor configurations, stricter emission requirements led to an embedded heating element being added to bring the sensor up to its operating temperature of around 250 degrees Celsius more quickly. Additionally, downstream O2 sensors were added after the catalytic converter to monitor its efficiency and detect degradation. Traditional oxygen sensors exhibit a narrowband, highly nonlinear response around the stoichiometric air-fuel ratio, and while this is effective for maintaining stoichiometric operation, this makes them unsuitable for measuring rich or lean mixtures accurately. Wideband O2 sensors, introduced in the late 1990s, overcome this limitation by using an additional oxygen pump cell alongside the sensing element. The pump cell maintains a constant oxygen level in a diffusion gap, with the required pumping current being proportional to the oxygen content over a much wider range, typically 10 to 1 to 20 to 1. This linear response enables precise air-fuel ratio measurements across various operating conditions, making wideband sensors essential for modern engine management systems, especially in contemporary direct injection engines, lean burn applications, and diesel engines where operation away from stoichiometric is common. By the 1970s, the need to meet emissions restrictions while simultaneously maintaining vehicle performance accelerated the industry towards fuel injection. These systems quickly evolved from simple O2 sensor-controlled electromechanical valving within a carburetor, ultimately to pressurized electromechanical fuel injectors that for the first time fully relied on sensors and electronic control to manage the entire envelope of engine operation. In order to reliably meter fuel into a gasoline engine, the precise amount of oxygen being aspirated needs to be known, as well as the load placed on the engine. Engine load affects air-fuel ratio targets. Higher loads, such as acceleration and climbing, need richer mixtures of around 12 to 1 for power, while lighter loads, such as in cruising, run leaner, near 14.7 to 1 for efficiency and emissions. Carburetors directly make these measurements by a calibrated interaction with airflow, the throttle plate's position, and fueling jets. The first fuel injection systems were able to replicate this functionality by simply measuring the air temperature, coolant temperature, an engine RPM pulse signal from the ignition system, and a new type of sensor known as a throttle position sensor or TPS. Throttle position sensors are rotary potentiometers that are mechanically coupled to the throttle plate. They use a multi-finger metal brush contacting a resistive strip, producing a voltage output typically from zero point 0.5 volts for closed to 4.5 volts for wide open throttle that directly correlates to throttle position. When combined with an air intake temperature measurement and RPM, both the aspirated air mass and engine load can be indirectly determined from the air density and the expected airflow rate based on the engine size and RPM. While resistive throttle position sensors were popular for decades and are still common today, non-contact variants that eliminate wear and contamination started to replace them in modern vehicles around 2005. Non-contact throttle position sensor systems utilize Hall effect sensor ICs with neodymium magnets that generate a voltage proportional to magnetic field strength through dielectric field sensing. The integrated signal conditioning circuits within the sensor IC provide temperature compensation and linearization, outputting a precise 0 to 5 volt analog signal with resolutions down to zero point 0.1 degrees of rotation. Modern sensors typically also integrate mechanical switches at the idle and wide open throttle position, and in drive-by-wire applications also incorporate safety redundancy as well as rate of change sensing. The late 1970s marked a major milestone in engine control technology with the introduction of the first true computer-based engine management systems. These systems allowed a new level of control and versatility by replacing mechanical control circuits with a software-based strategy that relies on data maps associated with sensor data to modify base operation maps that control actuated components such as fuel injectors. This allowed for fine-tuning of fuel output and eventually ignition control across a broad range of engine operation conditions. With computer-based engine management, new sensors would be introduced that more directly measured air mass and allowed for faster responding, real-time adjustments, as well as compensation for altitude and atmospheric pressure changes. With previous systems varying as much as 20% from ideal fuel ratio, this more accurate fuel mixture across all operating conditions enhanced performance, fuel economy, and emissions control across the entire operating envelope. Manifold absolute pressure, or MAP sensors, were one of the first air measurement sensors introduced. They function by measuring the absolute air pressure inside the engine's intake manifold. The sensor consists of a thin silicon diaphragm mounted inside a reference chamber with a vacuum or calibrated pressure on one side and the manifold pressure on the other. When pressure changes occur, the silicon chip flexes, causing its electrical resistance to change proportionally. This resistance change is converted to a voltage signal that is used to determine engine load, and when combined with intake air temperature, the mass of air entering the cylinder. MAP sensors typically output between 0.5 to 4.7 volts, with higher voltages indicating higher manifold absolute pressure, such as during wide open throttle, and lower voltages indicating the lower absolute pressures or vacuum experienced during deceleration with a closed throttle plate. During the 1980s, as manufacturers experimented with new methods to increase engine performance, such as staged intake tracks and forced induction, variability in the amount of air delivered into the cylinder made the inferred air mass measurement made by MAP sensors less reliable. The solution to this was the direct measurement of the incoming air mass. The first mass airflow sensors, or MAPs, initially used a vane-style design that measured incoming air volume through physical movement. These sensors contained a spring-loaded flap that would deflect based on airflow, with the deflection angle measured by a potentiometer to generate a voltage signal proportional to the airflow. While functional, vane-style mass airflow sensors had limitations. They created restrictions in the intake path, had mechanical wear concerns, and couldn't account for air density changes. By the late 1980s, the hot wire MAF sensor began to replace the vane-style sensor. This design uses a heated platinum wire, or film, maintained at a constant temperature, typically around 200 degrees Celsius, relative to a reference thermistor. As airflow increases, it cools the wire, requiring more current to maintain temperature. The electronic control circuit measures this current change and outputs a proportional voltage signal, typically between 0 and 5 volts, with idle airflow reading between 0.6 and 0.9 volts, and maximum airflow reaching 4.5 to 4.9 volts. The system provided real-time mass airflow data by accounting for both volume and density, since the cooling effect depends on the actual mass of air moving past the wire. Modern engine management systems often use both MAF and MAP sensors for redundancy and enhanced control capability. The MAF provides primary air mass data, typically measuring between 2 to 250 grams per second, depending on engine size and operating conditions, while the MAP sensor helps verify proper system operation through signal relationship verification and provides backup functionality. This dual sensor approach allows for more precise fuel delivery and better emissions control across all operating conditions and allow for more sophisticated engine designs that have more variability in their operation. Driven by the power of computerized engine management, the late 1980s saw the move to software control of the ignition system and the first experiments with variability in engine timing, initially through single cam phasing. Engines could now dynamically change their aspiration and combustion dynamics to best suit a broad range of operation demands all in real time. For this to work, engine management now needed a new class of sensors that could both rapidly and accurately convey the position of rotating components in order to make changes. The first position sensor developed was the variable reluctance sensor, which works on the principle that air has greater magnetic reluctance than iron. Still in common use today, these sensors typically consist of a permanent magnet with a metallic flux path and a pickup coil. When a metallic reluctor wheel attached to the component being measured rotates, it creates changes in the magnetic field, generating voltage pulses in the pickup coil. The frequency and voltage of these pulses directly correlate to the speed of rotation, with a pronounced voltage drop to near zero as the sensor passes the missing teeth. The voltage produced provides a precise and fast-responding rotational speed signal that can range from 0.5 volts to 70 volts, while the pulse component is used for timing determination. Variable reluctance sensors are a popular choice for crankshaft position sensors and are also used on simpler camshaft position sensors to identify the cylinder position. They're also used for wheel speed sensors in ABS systems and within transmissions for both gear and vehicle speed determination due to their reliable speed sensing voltage relationship and the ability to operate in high temperatures and in oily environments. They do, however, have lower speed limitations, typically around 100 RPM, with their peak precision of around 0.3 degrees of measurement being limited to a narrow operating speed range. At higher speeds, they also suffer from poor waveform generation and require signal conditioning. With independent camshaft motion, more accurate semiconductor-based Hall effect sensors became increasingly popular. Hall effect sensors contain a semiconductor chip that's sensitive to magnetic fields and a permanent magnet behind this chip. When a metal gear tooth passes in front of the sensor, it provides a path for the magnetic field to flow through. When the gap between teeth passes by, this magnetic path is interrupted. This alternation between tooth and gap creates a precise digital signal that indicates speed and position. Hall effect sensors have the advantage of producing constant amplitude signals regardless of speed, typically 5 or 12 volts peak. These sensors are also very fast, responding within 2 microseconds. They're also equally temperature and oil resistant as variable reluctance sensors and have no lower speed limit, providing rotational resolution down to 0.1 degrees at all speeds within an engine. Optical position sensing is also a lesser used technique. These use an LED phototransistor paired with a slotted disc to generate pulses. Though they produce a clean digital signal and are highly immune to electrical noise, they are sensitive to dirt and oil. They tend to be embedded within another component such as a distributor to shield them from contaminants. By the 1990s, computerized engine management systems began to increase all realms of engine performance across the industry. Higher compression ratios and more widespread use of forced induction were now possible. This was primarily due to a feedback system known as knock sensing that allowed engine management to safely operate closer to their theoretical performance limits while preventing destructive engine detonation. Knock sensors are mounted on the engine block, typically adjacent to the third cylinder on each bank, as this position allows it to best detect vibrations from combustion knock. The sensor utilizes a piezoelectric element which produces a small electric charge when it is compressed and then relaxed. The sensor's specific design includes a steel washer that acts as a seismic mass and a piezoelectric crystal element that is pre-tensioned by the sensor's mounting method. When combustion knock occurs in the engine, it creates mechanical vibrations that are transmitted through the engine block to the sensor. These vibrations cause the seismic mass to compress and relax the piezoelectric crystal, generating a small electrical signal that oscillates at the same frequency as the knock. The tuning of the sensor is critical because it must also be able to distinguish between knock from combustion and other normal engine mechanical noises across a cylinder bank. This tuning is based around the fact that combustion knock produces vibrations that fall within a specific known frequency range for a given engine block. When knock is detected, the engine management will retard the ignition timing by an amount sufficient to eliminate the knock. Once the knock ceases, it gradually advances the ignition timing back to its normal setting in steps. If prolonged knock is detected, fueling and boost will also be adjusted to prevent damage. This closed-loop control system not only protects the engine from damage while maintaining optimal performance, but also allows for safe operation with variability in fuel quality and octane rating. The 1990s also saw the addition of computer-controlled emission systems that utilize variants of existing sensors for their operation. MAP-like silicon diaphragm sensors, for example, are also used in evaporative emission or EVAP systems. However, unlike MAP sensors that use a sealed vacuum reference chamber, EVAP sensors use atmospheric pressure as their reference. These variants are calibrated for much smaller pressure variations in fuel vapor systems, typically around plus or minus 0.036 psi. This allows for the detection of fuel system vapor leaks by monitoring pressure decay rates relative to atmospheric pressure. The same silicon diaphragm pressure sensing technology has been widely adapted for fluid pressure monitoring throughout modern engines. In oil and pressure applications, the sensor design is modified with stainless steel diaphragms and isolation chambers to protect the silicon sensing element while maintaining accuracy. By the mid-2000s, pressure sensing would move from emissions and secondary monitoring to a primary operation sensor with the introduction of direct injection systems. However, while traditional silicon diaphragm sensors remain viable for low-pressure port injection systems, the extreme pressures of direct injection, often exceeding 350 bar in newer systems, drove the adoption of piezoelectric sensing technology. These sensors utilize crystalline materials that generate an electrical charge under pressure, offering faster response times and higher pressure capability than silicon-based sensors. In modern direct injection systems, piezo-based sensor pulses go through dedicated signal processing within the engine management system and provide real-time pressure feedback thousands of times per second to maintain precise fuel delivery across varying engine loads. This high-speed measurement capability is particularly crucial for multiple injection strategies where several distinct injection events occur within a single combustion cycle, requiring pressure monitoring and adjustments between each injection pulse. While modern vehicles now incorporate sophisticated sensor arrays that observe the environment through cameras and radar, and measure complex vehicle dynamics through integrated accelerometers and gyroscopes, the fundamental principles established by early automotive sensors remain at the core of internal combustion engine management. These systems are evolving towards sensors with integrated processing capabilities connected through modern vehicle networks like CAN-FD and Automotive Ethernet to reduce complex wiring, yet the basic needs to measure pressure, temperature, position, and chemical composition continue to drive development, showing how the pioneering work in engine sensing laid the foundation for today's advanced automotive technology. What fascinates me about modern engines is how they represent our shift from mechanical to digital thinking. What once required a calibrated moving mechanism has evolved into elaborate sensing networks, driving hundreds of software-driven decisions per second with near-perfect accuracy. This transformation of physical problems into mathematical solutions was bridged by the electronics revolution, and a great way to build an understanding of all the links in this chain is with Brilliant. Brilliant is where I discover the thrill of learning, offering thousands of captivating interactive lessons in math, data analysis, programming, and AI. What makes it truly special is how it transforms complex concepts into engaging hands-on experiences that build real problem-solving skills. What sets Brilliant apart is their first principles approach. Instead of just watching lectures, you're actively solving problems and building intuition. Each interactive lesson lets you experiment with concepts hands-on, a method that's proven to be 6 times more effective than passive learning. I love that all the content is created by leading experts from institutions like MIT, Caltech, and companies like Microsoft and Google, who know how to make complex topics accessible. Brilliant immerses you in active problem solving from the start, because truly learning a concept requires more than just watching and memorizing. You need to experience it. By engaging in hands-on learning, you'll not only build real-world knowledge on specific topics, but also develop critical thinking skills that make you a better thinker overall. What really works for me is how seamlessly Brilliant fits into my daily routine. Whether I'm waiting for coffee or on my commute, I can dive into a quick lesson and learn something meaningful instead of mindless scrolling. It helps me build a learning habit that actually sticks. A great starting point I highly recommend is Brilliant's Circuits course. In this course, you'll explore the physics behind electricity and how circuits actually work in everyday devices, with hands-on problems that make electrical concepts intuitive and practical. To try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/newmind or click on the link in the description below. You also get 20% off an annual premium subscription.